All right, so this is exam 2 review. There's lots to cover. And so there's the chain rule, but we're going to be using chain rule throughout the review, so I'm assuming that's the easy part, and we can just skip over that, right? Okay. All right, so first we want to cover implicit differentiation. And remember that's where x is considered the independent variable. So we're going to be differentiating with respect to x. And y is implicitly a function of x. Right? So naturally, if you come across f of x and you differentiate it with respect to x, you're going to write f prime, right? And if you have a function of x and that's inside some other function, let's say cubed, and you differentiate, of course, you're going to apply the chain rule. Okay. Just remember that they won't write f of x, just y is this unknown function of x. So for example, if we want to differentiate this with respect to x, and we know that y is an unknown function of x, we would, as always, just differentiate an exponential, and then times apply chain rule. And when differentiating the sum, we can differentiate term by term. And what rule do we have to use when differentiating x times y? Product rule, because we have x times some function of x. So product rule. So differentiate x with respect to x times y plus x. And the y prime is the best we can write. And of course, if you come across y, just write y prime. Okay.
Excuse me?
Yes.
What is the e term x, y plus y go on the right side?
Yeah, it's right there. You just didn't see it right away. Yeah. All right, so let's go ahead and do our first example. We're going to consider the curve in the first quadrant. And we want to find the equation of a tangent line. When x is 1. All right. So how do we, what do we need to do or have? What information do we need to get a tangent line, or any line for that matter? Well, we need a point, and we already know the x coordinate is 1. So how can we find the y coordinate? They might tell you, right? But let's just, for giggles, try to solve for y when x is 1. So when x is 1, we'll get a quadratic in y. So we're going to get y squared minus 2y minus 3 is 0. And we can, well, use quadratic formula or simply factor. So sometimes it's necessary, if you're given one variable, to go to the starting equation to get the value of the other variable. So here, y is either 3 or -1. And we're going to use the one that makes sense for the problem, quad 1, right? So y is positive in the first and second quadrant. Okay, so we have our point. And we're going to get our slope, of course, by using implicit differentiation So we need to get y prime and evaluate it at this point. Okay. All right, so towards that end, we're simply going to start using the starting equation here. We're going to differentiate the world with respect to x, right? This is our purpose in life this semester. And is it okay if I write prime with the understanding that it means derivative with respect to x as opposed to writing derivative with respect to x all the time? Okay. So we're going to, does anybody know why Optimus Prime is the mascot? They already used this show class? Why Optimus Prime is the mascot for Calculus 1? Does anybody see the wordplay? Okay. In order to optimize, you need to be able to differentiate according to Optimus Prime. Okay. So we'll go ahead and use, we could distribute the x squared, I suppose, but we can just use product rule, right? We have a function of x times, well, some function of x, right? Y is a function of x. Oh. What just happened? Is everybody okay? Should I call emergency services here? It's a joke, by the way, if you're online. Okay. So we differentiate the first factor, leaving the second one alone, and then leave the first factor on here. We're going to differentiate y squared, so we get 2y, but if we know that y is a function of x, the chain rule kicks in, and we write y prime. Derivative of 3 is 0. Okay, and then the other side, again, product rule, function of x times the function of x. So y prime, and then 3x squared. Okay. So at this point, we would pay careful attention, right? Because if they want y prime at a specific point, then it's smart just to plug in the x and y value at this point, right? But if they want a formula for y prime in terms of x, then we have to do some algebra. So let's, even though I should be plugging this in right now, x is 1, y is 3, just for, again, giggles, let's solve for y prime. So we are going to take any terms that have a y prime in them and bring them to one side. And I guess any terms that do not, we're going to bring them to the opposite side. Right, so just subtract that sucker over. And why did we do this? Why did we bring all the terms that have a y prime to one side? Well, because now it's a common factor in all terms, so that means it can be y prime can be factored out. Okay. Quotes. Okay. So if we wanted to solve for y prime, then we would divide by the coefficient that's multiplying, by coefficient I mean that expression that's multiplying y prime. Of course, we leave the other side alone. So I can ask you, what kind of thing could they ask you if you have this result? What kind of thing could they ask you for? It starts with h, for example, tangents. And so if they ask for horizontal tangents, what would be the next step?
Set equals 0.
Yeah, a horizontal tangents means the slope of the tangent lines is 0. So you just set y prime equals 0 and try to solve for x or y or whatever. I wouldn't want to.
Why is that symbol you put next to the, when you, about the, in the previous step, before the final step?
Oh, those quotes. So I wish I had a control D thing going on. I just wanted to rewrite that. I just want to drop it. I didn't want to rewrite the right-hand side. There you go. Okay. All right. All right, so, but we are looking for the slope at a very specific point. Anyway, if I were given that point, I would be plugging in the numbers at this point and not bothering the algebra, but whatever. All right, so x is 1, y is 3, so no reason to if I get 0 in the denominator, man. Okay. All right, so that looks like it's -3 over 4, right? So that's our slope. All right, we got our point, we got our slope, we got the equation of our tangent. Oh, this is not a touch screen. We got the equation of the tangent line. So point slope form. Right, so the y value was 3. We found the slope to be at -3/4. X was 1. And if you must, rewrite that in slope intercept form if they ask. 15 over 4 if you want to simplify. All right. Beautiful.
Wait, so the first step of this whole problem is solving the plugging the x equals 1 into the equation.
Yeah, just in case they didn't give you, like they might say, find the equation of the tangent line at the point 1, 3. They might just give that to you. But if they don't, this is also useful for related rates. You should be able to go back to the original equation, plug in one of the variables, and if the problem is designed well, right, you should be able to solve the other variable. So this one is similar, so I'm not going to actually do it. I'll just, I guess, put it in the solutions, but it's similar. Yeah, we'll have to, because it's logarithm. Okay. Okay. So did you guys like those problems where you had f composed with its inverse, and you derived, and what is this supposed to equal? When you compose a function with its inverse, what do you always get back? The original argument, right? You get the identity function. I'm going to pass you on the sign-in sheet. So, and this was the formula you derived was an application of the chain rule. So we just differentiated both sides with respect to x. I'm going to write prime. So chain rule says you differentiate the outside function, which is just f, leaving the inside alone, and then multiply by the derivative of the inside. Here the notation was really cumbersome because it's the derivative of f inverse, so you have these like almost, if you not careful, it looks like, I don't know what it looks like. But you have f inverse prime at x, right? And on the other side, you get derivative of x with respect to x is 1. And then we solve for the other way. Then we solve for this little thing. We want to isolate this on one side. So we just divide it over. Okay. And we got a nice little formula. You had some nice homework problems with this. By the way, whoever's designing your homework problems, I like it. We're going to encourage more of that, but. All right. So this is the formula we want to know. So okay. I think this works. So let's look at this function. And by the way, what has to be true for the inverse to exist near a point? For the differentiable, I guess, inverse to exist. Well, f prime has to be non-zero, right? Because you can't divide by 0. Okay. So let's go ahead and look at this little nice function. Okay. Number 1, let's compute f of 2 for a good reason. What is f of 2? Cosine of 2 pi is 1, right? Yeah. So f of 2 is 6. So can I ask you, what is f inverse, assuming the inverse exists, but it does. What's f inverse at 6?
2.
2. Right, so don't forget, if they're going to ask you to evaluate something like f inverse at b, just remember that if f at a is equal to b, then if function is invertible, then f inverse at b should equal to a, right? Yeah. So we're just making a note of that. So next, we're going to find the equation of the tangent line. At x equals 6, which is kind of confusing, but right. So what do we need? Well, we need a point on the graph. Oops, I didn't say tangent line to what, did I? To f inverse. Okay, that's the whole point of the problem. So we're not finding the equation of a tangent line for f, but rather its inverse. And that's where this theorem will come into play, because we need a slope, right, for the inverse. Okay, so what's our point? Well, we know that f at inverse at 6 is equal to 2. So our point on the graph is 6, 2. Remember that x here represents the argument of the inverse of the function, and the y coordinate is the result, right? So we have a point. So we'll then need a slope, and for that we need to find the inverse of the function's derivative at 6. And so we use our formula. It's 1 over the derivative of our original function evaluated at the inverse at 6. But f inverse at 6 is exactly 2. So we need to compute f prime and evaluate at 2.
If I may ask,
Yes.
how do we decide which value of f to compute in the beginning? Why are we computing f2 specifically?
Oh, I just didn't state the problem really well.
Okay, fair enough.
I said, find the equation of the tangent to f inverse when x is 6.
Yes.
But well, maybe we can do an example. But if I set this equal to 6, it'd actually be very hard to solve for x to find that's 2. So I kind of gave you a hint. F at 2 is 6.
So that means, so we find the function to find the inverse. You have to use the inverse point. That's how it works.
I'm not. What do you mean by inverse point?
I mean, so whenever you're finding the point, right? You have to use the inverse function to find the point.
Yeah.
Okay.
Yeah, because it's the tangent to the inverse of the function, right? At x equals 6. So the x value here is 6, and the y value corresponds to what the inverse function would output.
Okay.
Okay. All right. So, so we need to, if we have f of x, we need to compute its derivative and evaluate it too. So let's use, have you heard of the triple product rule? Does that even make sense to you? So what's the product rule, the template, right? You just write the factors, but you differentiate one at a time. But you can, like, inductively kind of think about it. You can do this over and over. So if you have 3 factors, you can convince yourself that you just write them down three times and you just differentiate one factor at a time, right? And you can generalize this if that makes sense. And that's what I'm just going to use here because I don't want to waste too much time. We have first, second, and third factor. Okay. So let's compute this derivative fairly quickly. Okay, so differentiate the first factor, leaving the other ones alone. Plus, now we're going to differentiate the middle factor, that exponential, and of course the derivative of an exponential, and then always chain rule. Always chain rule. Right. Finally, differentiate the last factor. So we get, I believe, negative pi sine of pi x and chain rule. And this is all evaluated at 2. So that's 3. It's going to be, what is that? 1, 1, that's 6 and negative 4. I mean, I have it written down, but it's 6, 0. This would be 0 because sine of any integer multiple of pi is 0, right? Sine of any integer multiple of pi is always 0. So that just goes away. So we get negative 21. Okay. All right, so then there we go. We have the slope is, right? Well, f prime at 2 is negative 21. So f inverse prime at 6 is the reciprocal of that. So what are they really saying, by the way, in this theorem? That the slope to the original function is exactly the reciprocal of the slope of the inverse function. That's all that's really, nothing too mysterious. Okay, so we put it all.
What did you just say?
I don't know. Can somebody repeat that because I forget it? Oh, all this theorem is saying is that the slope of the tangent to the original function and the slope to the inverse of that function are reciprocals. That's all it's saying.
The slope of the tangent to the which function?
Original.
The original function.
And the slope of the tangent to the inverse, they're reciprocals. Okay. All right. So there we go. Do we have a point and do we have a slope? We indeed do. All right. So what was the y value? 2. And the slope is negative 1 over 21, and then the x value is 6. And you can rewrite that if you wish. Can anybody guess what the, so this is the tangent to f inverse at x equals, oops, yeah, 6. Does anybody want to venture to what the tangent to f would be? Just by looking at that? Okay. Food for thought, right? Okay. All right, great. That was a good problem. I'm happy with that one. Oh. So the third example I'm not going to complete, but it's exactly the same story. You're given a function. If you want to practice, and then you want to find the equation of tangent line to f inverse at x equals 6 again. Right? So what would be different about this one, because this would be all the instructions I would be providing, right? What would be different is that you would have to figure out for which value of which argument for the original function would give you 6. That's a little tricky. I have to admit that's really confusing. because this x represents the argument for f inverse, not for f, right? Okay. But then you would have to set the original function to 6 and solve for x, and it's quite doable. You'll find that x is equal to 2. In other words, f of 2 is 6, so f inverse at 6 should be 2. So yeah, and did I actually write it out? No, I didn't write the answer. I'll include this in the answer group. All right. Good. All right. So what's next? Oh, do you all know how to derive the formula for the derivative of a log of a certain base, a base of some function?
We covered it in class, but we never actually did it. We never actually did that stuff.
Wasn't it on your homework?
Was it?
Was it? No. Okay. Well. Anyway, so just a reminder of the formula in case. So if we have the log base b of some function is equal to y, what's another way of rewriting it? Like you have this triad of numbers, right? If you have log base b of a equals c, that's equivalent to saying b power c is equal to a. So this says b to the power y is f of x. Oh, right. So maybe I should have started with. Okay, but what properties? What do we want to take advantage of here? Let's say in deriving the formula for the derivative of log of a different base. Just as a reminder of what. Well, I mean it's logarithmic differentiation, right? So what does a logarithmic differentiation allow you to do? It allows you to decouple kind of the exponent from the base by taking advantage of properties of logs. So you take the natural log of both sides. Using properties of logs, you can just bring that exponent in front of the log. And I'm assuming we learned how to differentiate natural log. I guess you would have to derive that somehow. So when we differentiate both sides with respect to x, right? Remember, y is a function of x. So this is an example of implicit differentiation. Well, sort of. Not too implicit, right? You get y prime and natural log of b is a constant. And then we all know the derivative of natural log is 1 over the argument of that log. In chain rule, puts a derivative in the numerator. And so now we can finally solve for y prime. So this rule for differentiating a log is exactly the one we would use for differentiating natural log, right? Except with natural log is what base, by the way? It's log base what? B, right?
Wait, so in this case, b is a constant?
Yeah, b is a fixed base.
Okay.
Yeah. So and we know the natural log of b is just 1. Okay. So this rule reduces to the one you're familiar with in the case where the base happens to be b. All right. Just as a reminder, I'm not sure if covered that.
Oh, can you stay on that for 30 seconds?
Yeah. So as a quick example, thank you. As a quick example, what if you have log base? What's your favorite base?
Big fan of 10.
Big fan of 10.
2 actually. Go with 2.
Too late.
2 is a classic.
2 is a classic indeed. So here, because the base is different, you just differentiate like any other log, put the argument of the log in the denominator, chain rule puts the derivative on top, and then but that little tweak factor, right, you have to divide by the natural log of that unnatural base 10. All right, and speaking of properties of logs, if you wanted to find the equation, I don't know why I'm obsessed with these tangent lines. To the graph, to this curve.
Maybe we.
Would it be smart to go ahead and differentiate this as it stands? Would we want to differentiate this using product rule, quotient rule, chain rule? Nah. So what do we want to do instead? Yeah, you have a bunch of factors, right? Factors, so log simplifies, log of a bunch of factors, whether it's multiplication or division. You can break that up using properties of log. So it's smart instead to take the natural log of both sides first. All right, and of course the properties we're referring to is that log turns a product into a sum of logs, and log turns division into the difference of logs. Log of the numerator minus log of the denominator, and it also allows you to bring down bring any exponent inside that log in front. So, of course, natural log of the e is 1, so that you all know that. So that's what we're going to do here. I first see a division in the overall. So we have log of the numerator minus the log of the denominator. And then we have a product over here, so all right. And over here we have an exponent, so we'll bring that in front. And can we? Is there a rule for simplifying log of a plus b? Or maybe is there a rule for this? Or this? I'm scared of just writing it. I'm scared to put the thought in your head. Are there any rules at all to simplify this? No. That's it. This is no simplification, right? Okay. Well, I better spell that out. Right. And likewise, there's no rule that says log of a plus b or minus b, whatever, simplifies. Okay. All right, but then of course we would get log of e of this function, so we get that exponent in front, and log of e is 1, then plus, and we know that square root is really what power? 1/2. So we'll save some time. All right, that's it.
Why didn't you break up the multiplication again?
Why did I break it up?
Why did you not break it up again, the multiplication?
Did I not?
In ln e to the power of 2 pi x times x squared plus 9 power of 1/2. Can't you break that up again?
I think I just did it too quickly, but I did. You mean this using properties of log break up that product?
Mm-hmm.
I think I did. I just
I think you just did.
I didn't verbalize it. So we had log of the first factor plus log of the second factor. And then you know, use that property there, bring the secant in front, it's an exponent, and log of e is 1. And here we brought the half, you know. X squared plus 9. All right. Man, 16, yeah, this better be well designed. All right, and what do we, okay, but that's the right-hand side. What about the left-hand side when we differentiate that with respect to x? When we use this logarithmic differentiation, what do we have to do? Well, chain rule, right? Y is a function of x. So the derivative of log of y is 1 over y, and then what times y prime according to the chain rule. So, yeah. All right. Okay, so when x is 4, what's the right-hand side? That's 1. Here we get 69, 25, so 5 squared, whatever. X is 4, so we get minus log 1, which is 0. Okay, so that's the right-hand side. But what do we have on the left-hand side? Do we know everything on the left-hand side? Or, well, we don't know y prime, but do we know y? Yeah, we can easily figure it out, right, by just coming back over to the original and asking ourselves, when x is 4, what is y? So I believe you get e.
Did you derive the whole thing yet, or just the left side?
Both sides. The right-hand side I differentiated to get this, and the left-hand side I differentiated to get that.
How did you derive it? Because isn't that when x squared plus 9 power 1 half the same thing as the thing below?
Oh, you said I didn't actually differentiate. Oh my, thank you so much. I forgot to differentiate. All right, now we differentiate. The left-hand side and then the right-hand side. All right, derivative of secant, I believe is secant tangent? Okay. I forgot to differentiate. So we get a half, denominator, derivative of the inside. Derivative of square root of x is 1 over 2 times square root of x. All right, great. So now we can plug in x equals 4. So we're going to get 0. This is going to be 4 over 25. Quarter, that's 1. Well, I don't know what that is. I'm not going to bother right now. But how do we find y? Now we'll go back to the original, right? When x is 4, I believe y would be, really quickly, e to the negative 1, right? No, hold on. It's e to the positive 1. 5e. Whatever, it is what it is. So y prime would be all right. Well, anyway, we found the slope. I'm not going to finish the rest. You know, the point we have. By the way, what mistake do you see most often if you have log of a times b divided by cb? I'm not sure if it's students in 2413 or some other calculus course, but right, when you have a quotient, so log will turn that into a difference of logs. What do people tend to forget here? They forget to they neglect the fact that this minus affects everything that comes after it. So it's smart to use parentheses. You would get log of c plus log of d. But then you would have to apply that negative to everything inside the parentheses. So that's a common mistake. All right. So use parentheses so you don't make that mistake or something like that. You often see incorrectly a plus over here, so we don't want to see that. All right. Great. Awesome. Okay. Well, let's move on then to the next topic. Where's my book? Which would be related rates. So this was example number 5. All right, so for related rates, we have some things that are changing with time. So things that are changing with time are functions of time, right? So here the independent variable is not x, it's not y, it's not whatever letter you use, it's t, it's time. So what are the steps, I guess, for related rates problems? Besides, reading the questions. Well, you want to draw a picture. I mean, when you draw the picture, how are you going to label it? What gets constant values and what gets like letter values? Well, things that are changing with time are functions of time, right? Are variable, right? So you use letters for those. Those are your functions. And things that are constant that don't change with time can get a number in the picture. All right. So I guess we can start with a simple one. Hey, could you take that call outside, please? All right. Yeah, let's just do a simple one with a maybe less in there. So, okay, airplane flies at a constant altitude. You've probably seen problems like this. Okay, and let's say that altitude is 5 miles high, right? At a speed of 400 mph, miles per hour. Directly, I should have just cut. Sorry about that. Directly towards an air traffic control tower. And we want to find the rate of change of the angle of elevation. So there's a lot of triangles from the tower. So that's going to be the angle relative to the ground when the angle is 30 degrees. And that's kind of mean of them to give you a degree, I think. Okay. So what would the picture be? Well, do you want? Is this plane going to fly east or west? Are we going to head to New York or California here? New York. Okay. So here's our plane. Here's the tower. I'm assuming it's short relative. Okay. All right. So it's heading towards the tower. Okay, and we're interested in the angle of elevation from the tower. So that naturally brings up a right triangle, which you see often. So the angle of elevation is going to be theta. Now they tell you what theta is, right? But why shouldn't I write 30 degrees there yet? I mean, it's intuitive, right? The plane, as the plane moves east, the angle will be changing with time, so that gets a variable name. Only after we differentiate do we start plugging values in. But what is constant is this altitude, 5, and the speed of the plane is 400 miles per hour to the right.
If they ask for the angle of depression, would that be from the top instead?
Yeah.
Okay.
Yeah, I think so. I mean, I believe that. Not that I went to like flight school or anything, right? But, all right. And okay, so all right. Right, so once we get a picture, we want to somehow relate. We want to relate the unknown, the variables, right? Oh, I forgot to label something. What am I forgetting to label? The distance, or the horizontal distance the plane is from the tower. I could also use hypotenuse if you want, right? That's another option. But why did I label? Why am I considering the horizontal distance? Because then we can think of the plane's speed as being the rate of change in x with respect to t. And what would that be? This could be tricky, but what would that be?
400.
Okay, what about, is it plus or minus? The way I do the picture, is it plus or minus?
It's plus.
No, it's minus.
Yeah, sure.
Why is it minus? Why is it minus 400?
Oh yeah, it's decreased.
Yeah, x is decreasing, right? As the plane heads towards the tower, x is getting smaller, so it's a decreasing function, so sometimes you have to be careful. Okay. So that's the given rate. And we want d theta dt. Do you expect that to be positive or negative? Positive, right? It looks like theta would be increasing as the plane gets closer to the top. All right. So once you draw the picture, you kind of see where you write the given rate and kind of make a note of the rate you want to find. Then you need an equation to relate the two variables whose rates you want to relate, right? So we want to find an equation relating theta and x. So what's the natural, well, what's the thing that we could do here?
Tangent.
Yeah, angle to sides of a right triangle, trig functions. And here we have the opposite side is 5, and x is the adjacent side, so tangent. So tangent of theta is opposite over adjacent. So 5 over x. Okay. Awesome. So now we're going to go ahead and differentiate both sides with respect to
Time.
t. Yeah. Remember, everything's a function of time here. T is the independent variable. So then the derivative of tangent is secant squared. And chain rule says to multiply by the derivative of theta with respect to t. Derivative of 1 over x times dx dt. Okay. So we got a picture. We wrote down an equation relating the variables whose rates we want to relate. And then we differentiate everything with respect to t. Okay, and they said the angle is 30 degrees. That's interesting. All right. How do we, so we know theta. I'm just going to write theta in radians. There's a danger that anytime theta like pops out of a trig function and multiplies something, not that we have this case, theta needs to be in radians. Radians relates angle measures to distances, right? So just to be safe, 30 degrees, we'll just write pi over 6 radians. I don't think it matters in this case, but. Okay, and we know dx dt is negative 400. That was the given rate. What is x? What is x? How do we find x? Right? I mean, I'll highlight the unknown, but there's still theta, d theta, dt, and then x. We don't know x, so how do we figure that one out? Yeah, you make a detour back to the original equation relating the variables. All right. So when theta is pi over 6 or 30 degrees, x would be what's tangent of pi over 3, by the way? Pi over 6. What is that?
I think the bottom is root 3 over 2, by the way.
I'm sorry?
I think the cosine is root 3 over 2, not root 2 over 2.
I'm so confused. All right, what's tangent of pi over 6? Somebody tell me before I. What is it?
1 over
Okay,
1 over root 3.
What is it?
Is it 1 over root 3?
Yeah. So root 3 over 3.
Yeah, all right, perfect. So 15. All right. So now we do know x. Right, so now we can plug and play here and solve for dx dt. So we get secant, right.
Excuse me. Do you think why you say you use radians again instead of degrees?
So if you have something like r times theta, okay, so that's, for example, is a formula for in a circle. If you have a radius and you want to find the length along the circumference, it's called s. You have r times theta. Theta needs to be in radians, because if you want to turn angle measures to relate angle measures to distances, you can't use degrees. So let's say the radius was 1, right? And theta is 30 degrees. This doesn't make sense. 30 degrees is not a distance along the circumference. But if you say pi over 6, then yes, that's a distance. It's a number. Here it really didn't matter. All right, so we plug and play, and then there we go. We get dx dt. Secant squared. What is secant squared of pi over 6? 4 over 3? And we know dx dt is negative 400. So indeed, d theta dt is whatever this number is, but it's positive. I'm not going to bother computing this. It looks nice, though. And that would be in radians per hour. Here the rates were in hours, so per hour.
I never actually got how x was equal to 15 by root 3.
I forget already. It was over here. Solve for x in that equation. Okay. What's another? Right, so you also need to probably know some formulas for surface areas and volumes, or do they provide those for you? I really don't know if anybody knows.
They don't provide.
Okay, so really quickly, sphere, area and volume. Area is, it's proportional to r squared, and it's 4 pi r squared. So if you take a circle, it's pi r squared, you can actually fit 4 of those on a sphere of that radius. Volume is 4/3 pi, and of course it's a volume, so it's going to be proportional to r cubed. Really, rectangular box, I'll let that one go. What about a cylinder? Assuming that in a cylinder everything is topped and bottomed off, right? So you're including the top and the bottom and the lateral side.
Hold on, sorry to interrupt, but where did the 4 by 3 come from? Previous question there.
I mean,
I want to follow
take multivariable calculus and then integrate over a sphere to find the line.
No, I'm saying in the previous question.
Oh. What previous question? This is a.
Oh, the related rates one. I'm not sure where you got that 4 by 3 dt by dt.
We'll figure it out later. Let's not worry about it right now. I'll post the answers. All right. So cylinder, what's the surface area? Well, it's 2 circles, right, on top and bottom. So, assuming it's not an open cylinder, so you get you get an area of a circle twice, because of the top and bottom. And the lateral side, of course, you can just unfold. The height, you get a rectangle, and the length of it is just the circumference of the circle. So 2 pi r. And the volume would be cross-sectional area of the circle, and then the height, like stacking points, I guess. So, and what about a cone, by the way? I don't know about the surface area, but how do you remember the volume of a cone? Anything conical, really. It's always 1/3 the volume of the cylinder it would fit inside, right? So it's just 1/3 the area, or 1/3 the volume of the cylinder it would sit inside. All right, let's see, let's do another example. 7. All right, so we have, I guess the red car is 15 miles north of the blue car. Simultaneously, the red car goes south. Make it simple, 30 kilometers per hour, I guess. Is that fast or no? That's pretty slow, isn't it?
Yeah.
And at the same time, the blue car goes, let's guess, 40 kilometers per hour east. So what's the rate of change in the distance between the two? Say after, let's just say 36 minutes have elapsed. All right. So we can start off, I would probably draw a picture just to the starting positions, right? We have a red and a blue car. The red car is 50 miles, sorry, kilometers. Okay. And then they're going to, at the same time, start heading off in their respective directions at their respective speeds. But we know that that's not the picture, that's not the dynamic picture, right? Because after some time, we're going to have the red car and the blue car somewhere over here. Conveniently, we can say the blue car goes along the x-axis while the red car moves down the y-axis. Okay. And we get another right triangle here. All right, so related rates often use Pythagorean theorem as well. So last time we used trig.
What happens when the red car passes the blue car?
They keep going. I guess they don't care. I don't know, unless they're, I don't know. What do you, like anything mathematically?
Yeah.
That would be a good question. We would say, what happens when, I guess, the red car is at the same altitude as the blue car? That would be an interesting question. That's another way to phrase it. It's good. What's more, what's more interesting would be the question, what's the closest they ever get? Would you think that would be when, actually, we don't know. All right. So we label certain things that are changing with time. So X and Y, so let's say that the position of the red and the blue car relative to the origin, right here. And we're also interested in the distance between them, so maybe we can label that Z. That's just the hypotenuse of that right triangle. And all of these get letter names, right? Because all these quantities are changing with time. There's no fixed thing here except maybe for the rates. All right, so we know we can relate the distance to the positions by Pythagorean theorem. So that's our equation relating the variables whose rates we want to relate. Okay, and yeah, okay, great. So what do we do next? Well, we differentiate everything with respect to time. Everything's a function of time here, so chain rule. Of course, I'm just going to divide by 2, right? I don't care about that too. Okay, awesome. So what is given? What is known? What is given? Well, what's given is dy dt and dx dt. And again, be careful with the sign over here. What's dy dt? What's the rate of change of the red car with respect to the origin, right? It's negative 30, sorry. Right, y is decreasing. So it's like kind of like your typical slipping ladder problem, which they love so much. So. And then dx dt, x is increasing, so it'll be a positive 40 for that rate. Okay. Well, we still don't know x, y, and z though, right? I mean, we want to solve for the, ultimately, this is going to be our answer, but we still need to know x, y, and z, so how do we figure that out? Well, what is x after 36 minutes? How do we figure that out? Speed times time is distance, yeah? So what's the speed of the blue car? It is 40. How much time has passed by? 36 minutes. So, and should we leave it as 36 or change it to hours? I think we have to change it to hours. The rates were given in hours, so let's do that. Okay, but this is minutes. So what's 36 minutes in terms of hours, by the way? 36 over 60? 6 over 10? 3/5? 3/5 of an hour, right?
Yeah.
Okay, 12, yeah, 12 times. So this is the 36 minutes is equivalent to 3/5 of an hour. So that will give us x. So that's going to be 24. So they traveled 24 kilometers. How would we find y? We know the speed of the red car.
You do the same thing with the other technique?
Yes. So we can say that y, right, the position, not distance, but rather maybe I should say position. So maybe we'll augment that, amend that, but y would be, well, the original position was 50, the initial position, and then the velocity is negative because we're going south, I suppose, times time. So after 3/5 of an hour have elapsed, where are we at here? Where's the red car at? So 32. Okay, so now we figured out that x is 24 while y is 32. That makes sense. Okay, perfect. Except what is z? Well, again, we know x and y make a detour back to this equation. And you get 24 squared plus 32 squared square rooted would be z. All right, let's not. So there you go, we know z. And then you plug and play there, so I need to find a new phrase. Well, it won't matter. Does anybody, can somebody compute this left-hand side?
Wouldn't we just be 40 because it's a triple?
Oh, dx dt is 40. So somebody want to compute this
I
side?
mean like z equals 40.
Z equals, oh, 30, 40, 50 triangle is what you're saying. At
Yeah.
3, 4, 5, yeah, I had probably, yeah, thank you. So does anybody see that this is a, is it? 24, 32. Is it?
Yeah. It's become 1600 and square root of 1600 is 40.
40? Beautiful, thank you. I don't know if it's going to matter that much. Right, because what is dz dt finally? Anybody have a calculator? Zero, thank you. So 0, if you solve for dz dt. So what does that mean, by the way?
because the 3 cars doesn't change?
The relative, yeah, like, so that would be the close, at that time, right, they're closest to each other, right? If z is the distance between them, obviously z will never have a maximum because they could just keep going in principle, right? So there's no maximum. So if you want to find when they're the closest, that you'd find the set the derivative of distance equal to 0. So it happens that they're the closest approach after 36 minutes because the rate of change is 0. That makes sense. All I'm saying is that z is the distance between them. It's a function of t. So if you want to find the closest distance using calculus, you differentiate, set that equal to 0, right? And solve for t. Beautiful. Well, I think that's it. So another thing that you'll probably see, you'll see this as similar triangles, right? So maybe have you seen this problem in class or text? You have a lamp post. And you have some person. And the light then casts a shadow of the person on the ground, right? And you might be given the speed at which the person is walking. So let's say you're given that the lamp post is 5 meters. And you're given that the person is about 2 meters. So those would be fixed quantities in your picture. And you're told that the person is walking at a speed let's say 0.7 meters per second. That sounds reasonable, doesn't it? And what kind of questions could they ask you? Well, they could ask you, for example, at what rate is the tip of the shadow moving along the ground? They could also maybe ask you, if you want to really play around, at what rate is the angle changing? So what is d theta? Another follow-up question. What is d theta dt when, let's say, theta's pi over 4 some crap, right? That's another question. All right, but to answer the first question, we probably will go into the second question. What would you label? Okay. Well, what's changing here is how far the person is away from the lamppost. And another variable might be, just be careful here, how far the tip of the shadow is away from the lamppost. Okay. Or you can alternatively label this y, and then, but that would be, well, right now this is y minus x, right? So when I say, so in this figure, if you want to use, you want to relate what? You want to relate dx dt. That's given. That's 0.7. That's how fast the person is moving away from the lamppost. And we want dy dt. How fast the tip of the shadow is moving along the ground. So I guess relative to the lamppost as opposed to relative to the person. Okay. So do you see how we can use similar triangles here? So what are similar triangles, right? Objects that have the same shape, if not the same size. So, or you can think of it as this theta would be the same for either this triangle or maybe the bigger one, right? It's the same shape. So the thetas would be the same. All right. So for example, tangent of theta for the big pink triangle would 5 over y. On the other hand, tangent of the same theta would be 2 over y minus x for the smaller yellow triangle. Or if you'd like, the ratio of the sides, right? Would be the same. There's lots of ways to think about that. All right, we have an equation relating x and y, quantities or variables whose rates we want to relate. And before differentiating, I'll just, of course, cross multiply. And then differentiate both sides with respect to t. That's sloppy, you know. And interestingly, there are no like x and y variables, right? So they didn't have to specify for which value of x or which value of y. Right, and we just plug in the rates. Hold on. This is easy peasy, no? We get 3 dy dt. It's 5 dx dt. Dx dt is 0.7. So whatever that number happens to be is 0.77. Right? Dx dt is 7 over 2.
Seven divided by 6.
Is it 6? Yeah, it is. Thank you. There we go. So now we know. And if you wanted the, well, heck, if you wanted the rate of change in theta, you already have a good equation here. The only tricky part is that you would have to have known, that to go, you have to find y prime, right? Yeah. But you would differentiate both sides with respect to time. So it's very similar to the previous problem with the airplane. And then if theta is pi over 4, you can figure out y, obviously. Oh, not again. Trig. Tangent of pi over 4 is 1, so y would be 5. That makes sense. You get a 45 linear triangle. Yeah, and that's it. You get 5 over 5 squared. Dy dt, we just figured out, is 7/6. Secant. 1/2. And then you can solve for d theta dt. Sorry.
So the tip of the shadow, that would be the whole entire triangle?
Yeah, so that's an ambiguity, isn't it? Because it's like because you have the speed of the shadow, the speed at which the shadow is elongating, that would be the speed of the tip relative to the person, but the person's also moving. And then there's the speed of the tip of the shadow relative to the ground, right? So relative to the fixed lamppost. So yeah, you could easily make a mistake there, right? Somebody wasn't careful in prompting the question. All right. And then, all right, I'm not even going to go into cones now. Okay. What's next? quick linearization stuff. Yeah, I don't have too much on that. So we know that tangent lines can be used to approximate a function near a point. So this is linearization. Differentials. And I guess we use those to approximate. Linearization is just another word for use the tangent line to approximate the function. So if you have a function and you want its linearization near a specific value of x, let's say a, let's use the letter a, then we can write L of x or whatever you want to use. And then you have what the function is at a, then plus the estimated change in the value of the function, and we use the derivative to estimate the rate of change, and then times the actual change as x moves away from a, right? So this is like the delta x, how far we move x has moved away from a. This is what the function used to be. Oh gosh, okay, let me draw it. So f of a, then you use a line, you have x, this is x minus a is like delta x, and this would be the approximate change in value of the function. So this would be f prime at a, the slope times the change in x to give you the corresponding change in y. And then we use that to estimate, well, this distance, I guess. So this would be what the function used to be plus the estimated change. Let's call it delta x. And that's, of course, different than what the function actually does at x, right? This is a mere approximation, not. So that's the linearization. It's an equation of a line, right? If you replace this with y, then you know you have an equation of a line with, yeah. All right, and yeah. So something really simple, because the only thing that could really go wrong is they give you a hard function to differentiate. But let's approximate something. I know this is an easy example. Whatever, I don't want to think about it too much. So how can we use linearization to approximate that?
X equals cube root of x.
Cube root, yeah, that's our function. Okay, and of course we have to notice that the number, the x here is 8.3, and what's really close by that's easy to cube root? 8, right? We know that cube root of 8 is nice. Cube root of 8 is nice. That's 2. So it looks like we should make a equal to 8. Okay. All right. So let's find the derivative of our function. The function is cube root f prime. Should I slow that one down? Or are you all okay with that derivative? Right, so f at 8 we know is 2. What's f prime at 8? What's 8 to the power 2/3?
4. I mean 1/4.
Yeah, so of course that's the cube root of 8. Then the result squared, so that's 2 squared or 4. Okay. It would be 1/12. All right, so we're going to write down the linearization here. L of x. It's what the function does at 8 plus the approximate change is given by the slope of the tangent line times the change in x as x moves away from 8. Plug in the particulars here. 2, 1/12. So that's our linearization. Now we can plug any x in that's close to 8. Right? The farther away is the worse probably the worse the approximation. (1/12), and this is 0.3, so that's 3/10. To 0.3. Yep, whatever that might be, 1/40. All right. So that's your approximation for cube root of 8.3. So if you're ever stuck on the desert island, you have methods. Okay.
So that's just approximation, right? If you want to find the actual, we just do cube root of 8.3 straight up like that.
Well, yeah, how do you straight up do cube root of 8.3 if you're on a desert island, I guess? No calculators though.
No food.
No food. Oh, I think I'm more worried about approximating square cube root of 8.3 than food. But, all right. All right. So, and what are, instead of linearization, what are differentials? So if you have a function, a differential, so y equals f of x, the differential is dy, and it's simply the derivative times dx. And this approximates the actual change in the value of your function. So it's an approximation. Right, if you replace dx with a number, a small change in x, if you will, that should approximate the value by how much the function has changed as you veer away from x. So the actual change is what the function is at x. Distance between the function is at x, and then x plus some little perturbation there. And that's the actual change in the value of the function, so delta y, but that's approximated by the differential. It's exactly this business, by the way. This is essentially it. This is like delta x, right, or dx. Yeah. So, and it's used, you probably used it already in your labs and stuff. If you have an error in the measurement of something and you're using a formula to calculate using that measurement, that error in measurement propagates in your calculation. So error of propagation. So here's an example. What example are we on? So, oh crap. This was 8. That's it. This was 9. You guys can go anytime, by the way. I know it's going to be a long day for me, so I'm going to finish this just for the sake of the video. All right. So the length of an equilateral triangle is, I don't know, 6.6 plus 0.02 centimeters, it says. So this is the measurement, and this is the uncertainty in the measurement due to whatever. So we're going to use differentials to approximate. Of course, and we can use computers now to get the actual error. the error in calculating the area of that triangle. By the way, what's the, if you have an equilateral triangle, let's maybe label the sides length x. What's the formula for the area of that triangle? Or how would you remember it? You drop a perpendicular, right? In a right triangle, all the angles are 60 degrees. Sorry. In the equilateral triangle, all these are 60 degrees. And when you drop that perpendicular, it's also an angle bisector, so you would get 30 and 30. So you get a 30, 60, 90 triangle. So here, 30, 60, 90. So if the hypotenuse is x, what would the altitude there be? Using trigonometry. Hypotenuse is x. This angle is 30 degrees, and we want to relate x to the side adjacent to that 30-degree angle. Which trig function are we going to use? Well, cosine does the job, right? Relating adjacent side to the hypotenuse side, just in case you come into for physics help next semester. So cosine of 30 is the adjacent side over hypotenuse. So the adjacent side must be x times cosine of 30, which I believe is square root of 3 over 2. All right, so then what's the area of a triangle? Half base height. Here the base is just length x. The height is that altitude that we've just found. All right, beautiful. So we have the formula for the area of an equilateral triangle. So now we're going to find the differential in the area for the dA. So remember, it's just A prime, if you will. A is a function of x, right? So it's A prime times dx. That's our differential. So what's going to play the role in the measurement? The measurement is x. The plus or minus is the differential error, if you will, right? 0.02. So we just plug and play. We plug in 6.6 for x and 0.02 for delta or dx, and that would be dA. And this doesn't give you the actual change; it merely approximates the difference, the error in measuring the area or calculating the area. All right. Again, easy enough if you just know the formula for differential. So just a quick reminder of linearization and what differentials do. All right, let's look at some choice problems here. And this is going to be max, min, and all that good stuff. Cool, so let's start with this one. So we're going to find, do you use the word local or what's the other word? Relative, max and min. Local. And instead of global, I believe, did you say local or relative?
Local and then absolute.
Well, if you're going to say local, why not just say then go global, right? As opposed to relative and absolute. Does that make them? I don't know. Okay, they're mixing metaphors. So find local, max, min, and then global or absolute. All right, and so what theorem guarantees that we're going to get an absolute max and min for this function on this interval? Well, what is this guaranteed by? Yeah, if you have a continuous function, and this is clearly continuous, it's just sines and cosines, and you're adding stuff. I mean, you're adding continuous functions. So it's continuous on a closed and bounded interval. Closed, I guess, meaning it contains its endpoints. Bounded is not finite in length. So extreme value theorem tells us that we are going to get absolute maximum. All right. So f of x, f prime of x. Oh, before I differentiate, what would you want to do, or what can you do here? You can use a trig identity, I believe. What's sine of 2x?
2 sin x cosine x.
All right, so let's find f prime now, using the product rule. Okay, and what are we going to do with that derivative? What is our job? Number one, we're going to find critical values, or critical points, I guess. On the inside, there are relevant inside the interval that interests us, right?
I think you forgot to derive 2 sin x on the right side.
Oh yeah, that's right. So the derivative of sine is cosine. That's right. Thank you. Find critical points inside that are relevant region. And then for a closed and bounded interval, we also always have to consider endpoints. All right, so I think the only way we're going to get critical points here is if this derivative is 0, because this derivative is always defined. And, oh boy, so just some trig identities, rewrite everything in terms of sine or cosine, right? Yeah. So we're just going to rewrite sine squared as 1 minus cosine squared. So that way, we're only dealing with one trig function. So, 0. All right. And do you see that this is a quadratic in disguise, right? It's a quadratic in cosine. And so if you had this, you would have no problem. I can divide by 2, actually. So I believe this factors. Or quadratic formula. Yeah, that looks good. All right. So here, either cosine is going to be a half, or cosine is going to be -1. So x, where's cosine half? pi over 3 and 5 pi over 3. And we're still sine negative 1 at pi. Okay. So those are the 3 critical points inside our region. All right. So we take the x-axis and we're restricting our world to this interval. And we have some cut points. Wrong class. We have some critical points. Anyway. So if you're just looking for absolute max and min, what could you do? If that's all you're interested in, right? Well, if for absolute max min, all you have to do is plug in all these points into the original function. Together with what? The endpoints as well. Right? So 0 and 2 pi as well. All right, so we calculate all these, and well, I don't know what that is. Let's sign up 10 pi. So how many? It's a pi and a third plus a negative. Anyway, so what's the absolute max and what's the absolute min? I believe the absolute max is 2. It happens at 0 or 2 pi. And the absolute minimum, I guess, would be negative 2. I'm guessing. At pi. All right, and if you wanted to know where the function is increasing and decreasing, we're not going to do that, right? But what would you have to do? Well, you would just choose test points from each. You cut up the number line using your critical points, then you just choose a test point from each interval and you plug it into the derivative to see whether the function is increasing or decreasing. It should be, right? So let's see, it's 0. Yeah, oh no, let's skip that one. Let's do something better. Let's look at increase, decrease, maxes, mins, and concavity and points of inflection. Something simple enough. Cool. All right, what's the domain of this function? It's all of the real numbers, right? You can take cube roots of negative numbers. So. And why do we kind of want to eyeball that domain? Is because we know that what does it mean to be a critical number of a function? So critical number, critical point, whatever you want to call it. Well, you have to be in the domain of the function in the first place, because critical points are candidates for where we attain extrema, where the function attains extrema. So if the function doesn't exist there, there's no extrema to take, right? Does that make sense? So you have to be in the domain of the function. And you're going to be a value of x that either makes the derivative 0 or it makes it undefined. All right, so let's look at increase, decrease. So of course the first derivative speaks to that. So first derivative. Product rule. Okay, power rule followed by a chain rule, which gives you a factor of 1. Right, so how are you going to deal with this situation? I think it's sort of difficult, right, to check where this is 0 or, well, no, it's not easy. It's not hard to see where this is undefined. You can even just set it equal to 0 and get it that way, but I'm just going to find this common denominator. Just anticipating that we might have to compute the second derivative for one reason or another. So multiply the top and bottom by all that. Right. All right, so when is this derivative equal to 0? When x is 6, right? When is this derivative undefined?
At 10.
10. And is 10 in the domain of our function? Yes, so it is a critical point. All right, so those two values are going to cut up our number line, creating 3 subintervals, or 3 intervals. And now we're going to see where the function is increasing or decreasing. So we have the interval.
I don't.
Yes?
Oh, we didn't put 10 down on the number line.
I'm sorry?
You didn't put 10 down on the number line.
Oh. Oh, I see, I see. Yeah, I mixed a couple things up, yeah. So the two critical points are 6 and 10. Thank you. So if you have 100 critical points, how many intervals are you going to get? Right, that's too easy, sorry. And then we're going to stick the test point from each interval, stick it into our derivative, which should say then something about our function. All right, 0 is a really nice number. What's f prime at 0? Is it positive or negative? Here's f prime, guys. Factored. Factored is better if you're checking for whether something's negative or positive. So that would be positive, right? Yeah. So that's positive. Cube root of a negative number is negative. So that's going to be a negative divided by a negative is a positive. So this means our function is increasing. So f prime is positive, therefore f is increasing. All right, another test point like 7, I guess. The numerator is positive, the denominator is still going to be negative, so negative. And I'm assuming that, yeah, if x is really large, let's say x goes to infinity, you see that you get a, so let's choose the x value like 1,001,230, right? Doesn't matter. Obviously, if you stick that into your derivative, you're going to get a positive number. Awesome. Okay, so by looking at the slope chart, if you will, what can we conclude so at x equals 6, what happens? Right.
Local max.
Yep, local max. And so you kind of want to maybe be careful. Like they might ask you, where does it happen? Or they might ask you what the function's value is there, or both, right? So local maximum, f is a local maximum of f of 6, which is I don't know what that would be. It's positive. And at 10, x equals 10, f has a local minimum. All right. Okay, so then what if they ask you about concavity? So we know that's the second derivative that speaks to concavity, right? So we need to compute if we know f prime, yeah, 1/3. Was that 1/3 or should it be 2/3? Right, then we can compute f double prime. So I guess that would be either product or quotient rule. I'll use quotient rule. That's some ugly stuff right there. Okay. Right. Anyway, hopefully that's right. All right, but so what do we want to do to find concavity? Well, second derivative positive means concave up, right? Second derivative negative means concave down. And so if you have a nice continuous function, we just need to find where the derivative, second derivative is 0, so right, neither concave up nor down, or undefined, I guess, so 0. So x is 0, I'm sorry, the second derivative is 0 when x is a what? Negative. All right.
So inflection points are when the second derivative equals 0 and not undefined.
Well, no, x equals 10 is also a possible x value where you have a point of inflection. How do you define point of, what's the definition of point of inflection? It's a point on the graph of the function, so x has to be in the domain, where there's a change in concavity. It doesn't have to be a smooth change, if that makes sense.
Okay.
So the function's domain, f, the original function, has domain all real numbers. So there's a possible change in concavity at x equals 10.
I also had a question for increasing and decreasing.
Yeah.
So it goes from increasing, decreasing, then increasing, right? But say, for example, it went increasing, decreasing, then decreasing. Then would you say it's decreasing from 6 to 10, and then unison 10 to infinity?
Like, so you're thinking of maybe you have some critical points, and you're saying that the function is increasing, and then what?
Decreasing and decreasing.
So the question, your question is, how do you answer? What's the answer to the question? On which intervals is the function decreasing?
Yes, sir.
So you'd say f is decreasing. Right, because the reason this is a critical point is because either the derivative is 0, so the function is neither increasing nor decreasing, at least instantaneously, or the function doesn't have a slope there, if that makes sense. It's not even, or it might not even be defined there. The function might not be. So you'd say on the interval from a to b, and you want to exclude b. So you would use that notation, I guess.
Okay.
Or you can use, if they ask for the intervals in which it is decreasing, you can just use a comma as well. As opposed to like you're just saying the f is decreasing on this set of numbers, so you can use a union symbol. Okay. Yeah, and then of course you wouldn't have a max, yeah, because it's there is no change, right? And slope, there is no max nor min at b at x equals b. So think. Anyway, that was an aside. All right. Beautiful. So on our number line, oops. On our number line, for the second derivative, we would get -3/2 and 10. Okay, so that gives you 3 intervals. And the second derivative, would it be positive or negative on the first interval? Let's say if we use -2. Do you see why it would have to be negative just by looking at the second derivative? What do we know about the factor in the denominator? Well, we notice that it's always going to be positive, right? Because at the end of the day, it's something raised to the power 4. So only the numerator will determine. So f must be concave down. This is the second derivative. It's negative. All right, a number between a negative and a positive, so 0 is good. So that's going to be positive. And greater than 10, it's still positive. So that's fascinating, right? That's exactly the example we want to see. Because just because the second derivative is 0 somewhere or undefined doesn't mean that we have a change in concavity. We actually have to test concavity using the second derivative. So is this an inflection point? I'm not going to calculate what it is, but is this an inflection point? Point of inflection?
Yes.
Yeah, because there's a change in concavity. This is in the domain of the function. So is this a point of inflection? No. There is no change of concavity. It's concave up on either, the function is concave up on either side of 10. All right. Okay, if you feel like leaving, that's fine, including you, Curdy. If you need to be somewhere, I appreciate all your help. But I'm going to keep going so for the video. Boring, boring. All right. Maybe one more. I skipped a whole bunch. I might just include them on the packet that it's going to be attached to the video. So one more thing. All right, so same business. Here's a function: increase, decrease, concavity, points of inflection, and so on and so forth. That's the easy one, but it's good practice. Okay, so quickly, what's the domain? What's not in the domain of the function?
3.
All right, so we have that. So x equals 3 cannot possibly be a critical point because it's not a candidate for where the function attains an extrema, as your function doesn't attain frat there, right? So it looks like a quotient rule is in play. And the only reason I guess I'm doing this simple one is that when we cut up the number line, are critical points the only things that cut up your number line when using the first or second derivative test? Right. So the two critical points are going to be 0, x equals 0, x equals 6. And we know that 3 is not a critical point in the strict sense, because it's not in the domain. But when we cut up the number line, if I do this, is this completely right? Well, no, we have to cut up the number line, not only using critical points, but singular, where the function has vertical asymptotes, right? With the denominator. Using critical points, and let's just say, I guess, because I'm not sure, and vertical asymptotes. Okay. Right, because when you have a vertical asymptote, your function can behave different, right, on either side. And when I say wildly, I'm trying to make math sound more exciting than it is, I guess. But you don't know, like, on either side of the vertical asymptote, the function might behave completely differently. So you have to use the vertical asymptote as well. So this would define 4 intervals, sorry. And then we can test, right? On the first one, the first derivative would be positive. Negative here. Negative, interesting, right? So positive. So the function is increasing, decreasing, decreasing, and then decreasing. So you get a local maximum at 0 and a local minimum at 6. And then you would go for concavity. Yeah, try concavity at home. I'll post the answer. Hopefully I'll have this typed up by tomorrow morning. Because, what else do we need to do? Let us, do you guys want to do some L'Hopital's rule? Limits using logs and stuff? Mean value theorem? Do you guys want to do mean value theorem? All right, so let's do one of those. All right, so yeah, mean value theorem. Let's do that first because that sounds like fun. All right, so what are the conditions for using mean value theorem? Or the most valuable theorem, right? Okay. Mean value theorem. What are the conditions that need to be met before the mean value theorem even applies to a situation?
Continuous on bracket A to B bracket.
Yeah. So f is continuous on the closed interval, so including the end at the endpoints. You can't have the function flying off in vertical asymptotes at the endpoints. F is continuous on the closed interval and differentiable, but on the open interval. And then mean value theorem applies, and what does it tell you? It just tells you that the slope of the secant line through 2 points is equal to the slope of a tangent line for some point in between, right? So it says that the slope of the secant line, change in y over change in x, is equal to the derivative, the slope of the tangent line at some point c, where c is in that interval from a to b. And there might be multiple values of c. Right? There's at least one of these. Right, and what about Rolle's theorem then? Rolle's theorem is just a special case of mean value theorem. And why is it special, right? What makes it, right, if I just copy this, Rolle's theorem would just have an extra condition that needs to be met. All right, I'll just move that in. Condition 11. Right, Rolle's theorem is just when the secant line is horizontal. Right, so we have to have the additional condition that f of the a is the same as f of b, so that the slope of the secant line is 0. If you're interested in why it's called mean value theorem, the other one's Rolle's theorem, well then you probably want to be a historian, right? Oh, f of b equals f of a. So that way the slope of the secant line is 0. And so then Rolle's theorem just says that there's some point c at which the slope of the tangent line is 0. All right, so let's just do a simple one. So here's a function. Apply Rolle's theorem on the closed interval from 2 to 3.
Wait, can you scroll up for a second? I have a question about mean value.
Yeah.
Is it does it apply for at least one seed within the open interval or the closed interval?
I mean, I use closed interval because what if you have that circumstance where your function is, let's say, a line, right? You know what I'm saying?
Okay, yeah, got it.
Then it's also, yeah, or it's constant. Then it's, I guess you can use open interval in those cases as well. I see what you're saying. No, you're right. Why is it open? Why do I have to say open? You're right. It's not like logically incorrect, but it's more appropriate maybe to say open. Why?
Like not including the points.
Because we said that f is differentiable on the open interval, so there's nothing guaranteeing that f prime at a or b exists, right? So I guess technically you're right. I like that. All right. Yeah, let's change it. It's a good one. Good thinking. All right. All right, so does the mean value theorem apply? Well, where this function is discontinuous where?
On 0% interval.
Yeah, at 0, but of course that's not in our closed interval. Number 2, is it differentiable on our interval? Well, let's just differentiate, and it looks like so. It's the derivative is only undefined at, again, x equals 0. Well, the function doesn't even exist there, so. But at least you want to acknowledge that, even if it's just a simple look at the derivative. It's defined everywhere except for the point, which is not in our interval. So the mean value theorem applies. So we're writing what the mean value theorem now guarantees, tells us what we need to compute. All right, so it looks like we need to f at 3, f at 2. All right, and f prime at c. All right, so let's see, f of 3 minus f of 2, all divided by 3 minus 2. Yeah, so I'm just rewriting this with the specific numbers plugged in. Yeah, and then we can find all values of c here. So c would be plus or minus square root of 6, except, right, we just want to keep the one that's in our interval that's guaranteed. So this is not in our interval, but this is, right? So we'll keep that one. And you can then check that you can, this problem is also good for Rolle's theorem. On the interval from, let's say, 1/5 to 5, where any two numbers that are reciprocals of one another, so you can probably see why. So Rolle's theorem would work here. Okay, so try Rolle's theorem. on that interval, that would be an answer. But maybe a more interesting use of mean value theorem, right, is inequalities. Did you have mean value theorem problems with inequalities on your homework? I think that's your class.
No.
No? It's 2417? So you didn't get questions like, let's say f of 2, so just a quick example, I want to see if this is familiar. F of 2 is 5, and they tell you something like f prime at x is less than or equal to 1 for all x. And then they want you to estimate or prove a certain inequality, find a bound.
Oh yeah, we did for one question.
For one, do you think it's, okay. Right, so prove that f of x is less than, well, let's prove that f of 5, no, f of 7 is less than or equal to 10. Again, it's not a mystery what's going on here. At 2, they tell you the function has value of 5. And whatever the slope of your function is, right, it's going to be less than 1. So if you had so whatever the graph is, at 7, f of 7 has to be less than what the line would say. Okay, the line would say that this would be 10. Okay. But you can use mean value theorem, just to consider f. Then I would have to do, obviously this means that the function is differentiable if I write that. And if it's differentiable, it must be, what differentiability implies what? Continuity, so it's continuous as well. For all x, right? So me writing that, they probably say, but f prime, since I wrote that, it must exist. It's differentiable everywhere, so it's continuous everywhere. Specifically or in particular on this interval from 2 to 10, right? And that's obvious why 2 to 7. That's obvious why we want to choose those numbers. So let me kind of write what the mean value theorem says. Slope of the secant one is equal to the derivative of the function at some point c, which is between 2 and 7. Do you see how the mean value theorem result, which has an equality, then can turn into an inequality if you know something about the bound on the derivative of the function, right? So we know that this derivative is at most 1, and that's it. No problems, right? Because the derivative is at most 1, but the derivative is equal to that, so that is equal to, is at most 1. And then you just rearrange. F of 2 was 5, multiplied by 5. Yeah, it works. Okay. So for giggles, maybe you can, if you're into fun math, for x equals positive, what's the standard problem? Use the mean value theorem to prove that inequality. But maybe that's for another time, right? On the weekend while you have at your leisure. So use the mean value theorem to prove this inequality.
This is the weekend.
But it's not leisurely for me, at least. I don't know about y'all, but it feels like work. I'm saying on your own in a napkin in a cafe. So, but I should skip that because that's probably too hard for a test. So, and just a quick conceptual question: would the mean value theorem apply to this function on this interval? answer's quick, right? In your head, you can differentiate that. I mean, the function is continuous everywhere.
No, it's not differentiable at 0.
Yeah, if you actually bother to write down the derivative, you figure out that you might get a 0 in the denominator, right? So f is not differentiable. All right, this derivative does not exist at x equals 0, and that's in our interval. So mean value theorem does not apply. However, could there still be a point where the derivative is, well, equal to the slope of the secant line? Maybe. There's nothing stopping it, right? So there's no guarantee because the mean value theorem doesn't apply. But there might be. So what's f of 8? F of -1. It's going to be 9. The derivative of c. All right. So you get 3 over 9, or 1/3. Yeah, so c would be, I don't know, c would be plus or minus 1, right? So 1 in particular. So c could be plus or minus 1. So 1 is inside that interval. Right. It's not contradicting the mean value theorem. The mean value theorem just simply didn't apply, so it didn't guarantee such a c, but there still might be. Anybody a math major here? Cool. So what else did we need to talk about? Right. So constrained optimization. Oh, I said L'Hopital's as well, right? Let's do that. All right. So how many indeterminate? Well, let's just look at L'Hopital's rule. So for what kind of indeterminate forms for limits does L'Hopital's rule apply?
3.
Which one? How many?
3.
Which ones are those? I just know 2.
Oh, 0 and then infinity over infinity minus infinity over infinity.
Oh, okay. So yeah, if you get something like 0 over 0, right, as an indeterminate form. Or infinity over infinity. Or plus or minus those, right? Whatever, it doesn't matter. These are indeterminate forms which are L'Hopital friendly. So you can apply L'Hopital. Okay. And if you get 0 over 0 or infinity, when we apply L'Hopital's, we just differentiate the top and the bottom separately from one another. No quotient rule. And if the limit exists, then we will get a limit, even if we have to repeatedly use L'Hopital's rule, because there's nothing stopping us from getting 0 over 0, infinity over infinity again. Okay, what are some other indeterminate forms? You get infinity minus infinity, which sometimes can be turned into L'Hopital's rule. Is infinity plus infinity indeterminate? If you take 2 oceans and put them together, you still have a big ocean. But infinity minus infinity, that's not the kind of arithmetic doesn't work with infinite numbers. So we don't know. We have 2 things infinite, they're vying with each other, and we don't know which one wins. So this is indeterminate. And sometimes you can if you have 2 separate, you can maybe combine that into a single fraction or something, and then try L'Hopital's rule. What about 1 to the infinity? That's indeterminate. But that's, if you get something like that, that's typically where you have a function of x as a base, a function and an exponent, a function of x as the exponent, and that's kind of difficult, right, to work with. So in those situations, what do we typically do?
Natural log.
Yeah, to take it, decouple that exponent from that base using properties of logs. And then maybe you can turn that into a L'Hopital's rule problem. We'll look at examples. 0 to the infinity is very much determined to be 0. 0 to the 0 is indeterminate. Gosh, what am I'm missing so many probably, right? Anyway, those are the ones that are kind of. So let's look at an example where we're not going to take logs really quick. This is a simple example. Oh, 0 times infinity. Or minus infinity. That's also, you have two factors, one going to 0, the other going large. When you multiply them, what wins out, right? Yeah. All right, so what kind of indeterminate form do we get here? Well, x infinity squared, so to speak, is infinity. And then you have 2 over infinity squared was like 0, right? So you have infinity times 0. Make sure that's clear. Okay, so can we, what do we have to do to get this indeterminate form into a L'Hopital friendly indeterminate form?
Divide by 1 over x squared.
Yeah. Essentially, you're taking advantage of the fact that if you have a non-zero number, you can rewrite it as the reciprocal that's reciprocal, right? The flip of the flippity flop of the whatever, reciprocal of the reciprocal. So we're going to take, let's say, this term, the simpler one, and we write it as 1 over its reciprocal. So it's 1 over the thing in the denominator. Right, and so now when you evaluate it, you're going to get 0 over 0. Oops. Which is indeterminate, but it's L'Hopital friendly indeterminate. So let's use L'Hopital. Differentiate the top. Differentiate the bottom. And then simplify. Notice the x cubes will cancel. Negative 3 by negative 2 is 2. So that's just a very quick example. Right, and then this limit is very much defined. 2 over x squared will go to 0. Cosine of 0 is 1. So the answer is the limit is 2. Okay, and maybe once and for all, if you're STEM people, if you have a polynomial, we'll do a specific example, and then an exponential, and you're looking at, that doesn't matter. Let me actually write down what I wrote down. Sure, yeah, it doesn't really matter. Okay, something to do. So if you have a polynomial times an exponential, and x is either going to plus or minus infinity, which factor will always win out? Like which factor determines the behavior, the long-term behavior? It's going to be the exponential, right? So if the exponential goes to 0 at infinity, then so will polynomial times exponential. And so we can use L'Hopital's rule. So let's do an example. This is for the scientists. Whatever, doesn't matter. Right. So right now, this is what kind of indeterminate form do we get? Well, where does the polynomial go as x goes to infinity? It goes to infinity. And where does that decaying exponential go? It goes to 0. So you have infinity times 0. So we're going to try to make this rewrite it so we get a L'Hopital friendly indeterminate form. So which thing was going to go to the denominator, do you think?
E to the power negative x.
Yeah, it's the simpler thing. All right, so then when we evaluate directly, we get one of those L'Hopital friendly indeterminate forms, so we go ahead and use it now. And here, this is an example, you just use it multiple times. Right? You differentiate the top, the bottom. I could have made it more fun if I put a constant in front of the x there in the exponential, but oh well. We still get infinity over infinity, but the point is just keep going. Right? 18x plus 2. Well, we're almost there. You still get infinity over infinity. And again. Yeah.
18 upon x, and that's
But that's it, right?
0.
Because
That's
8,
zero.
the numerator sticks, but the denominator is now growing exponential. So you get finite over infinity is up to 0. So the answer is that this goes to 0. So indeed, the exponential is always good. The exponential's behavior is going to determine the behavior of polynomial times exponential. You can even go to positive infinity, it still works. Okay. All right, maybe an example of infinity minus infinity really quick and what to do there. Uh-oh, I thought what did I just close?
I think you're drawing down.
All right, there you go. I'm gonna have to reshare OneNote here on. Oh. Sorry, I gotta fix this for the online. Okay, there we go. This is really painful here. Okay. There you go. All right. Okay, so x is going to 1 from the right side for probably a good reason, but so what happens to the first term? You get 1 over slightly positive 0, right?
So infinity.
Yeah, you get infinity. And the denominator here, as x goes to 1, though this goes to positive 0, this goes to positive 0. Oh, well, that's crappy. You get 0 over 0. Well, okay. So let's do something. It's supposed to be infinity minus infinity, but that's okay. Let's just combine. Suppose we did, for the sake of argument there. And what would we want to do if we want to use L'Hopital's rule, perhaps? We'll just combine these two fractions by introducing a common denominator. There you go. Right, so now when we try to evaluate, we're going to get 0 in the denominator, and we would also get 0 in the numerator. So that's a L'Hopital friendly indeterminate form. Anyway, that's an example of, well, that example of infinity minus infinity is supposed to be. All right, so you differentiate the top, product rule. Differentiate the bottom, product rule, I guess. And then try to reevaluate the limit. What do we get? What do we get? We get 0 over 0. Yeah. Differentiate again. Or use L'Hopital's rule, I should say again. So, yeah, just be ready to use L'Hopital's multiple times. So now when x goes to 1, on top we get -2, on bottom we get 3, so -2/3. It's supposed to be -1/2. Anyway, I would check that because I'm getting -1/2 on my card. What did I miss? Oh. Yeah, I was right. This was 4. I just forgot to differentiate this term. It's all good now. Well, okay, so it's -1/2. All right. So yeah, infinity minus infinity maybe combined into a single fraction. Maybe then you can use L'Hopital's rule. All right. So the next type of L'Hopital's rule problem would be 1 to the infinity kind of indeterminate form. That's when we take logs. So it could come in this flavor. I forget what these are. If somebody can guess what these are, or like order them from smallest to largest, that would be quite a feat. That'd be kind of cool. If you can think about these. Okay. Now I'm just going to do one of these, but I believe this is going to, you can check, but this is going to go to 0. This is going to go to e to the -1. I don't know what this is going to go to, but I probably 1. Okay. So how would we, in any case, when we evaluate this directly, what do we get in all these cases? Did I write these correctly? Oh, that's supposed to be infinity. Yeah, that makes sense. That makes sense. Plus infinity. So in all these cases, we get 1 to the infinity, which is an indeterminate form. And let's try this one first, because it's just a standard 1. You probably won't get that one. You're going to get something like something that looks like this. Okay. Does anybody know what this is? Top of your head. It's e to the a times b. But let's put that into, right, so evaluating directly, we get 1 to the infinity. So what we're going to do is, how were you taught in class? Were you taught to simply leave it like this, and then think of it as e to the log? Or were you taught to say, let y equal 1 over 1 minus x to the x, and then take the log of both sides? Can we assume that it's, so we're going to let our function, let's call it y. Then we take log of both sides, right? Because we want to decouple, again, it's the base and the exponent here are functions of x. So using properties of logs, right? Technically, log of this to the power x. Property of logs allows you to bring that x in front. Okay. So now we're going to take a limit as x goes to infinity. On the left-hand side is going to be the limit of a log of y. And we're just going to focus on the right-hand side right now. We get infinity times 0. Not quite, it's indeterminate, but not quite L'Hopital friendly, but we know that infinity times 0 can be turned into 0 over 0, infinity over infinity. We're just going to rewrite one of the factors as the reciprocal of the reciprocal. So reciprocal in the denominator. By the way, I wrote this down so you can create your own darn problems. And that would be actually the same if you want more variety. Maybe you can think about why that is, right? If you want to create your own exercises. All right, we get 0 over 0, so we can apply L'Hopital's. Differentiate the top. Maybe I should take that more slowly. All right, so differentiating the top, the derivative of log is 1 over whatever's sitting inside of log. And then we differentiate the inside. So don't forget that we have 1 minus x to the negative 1. So when you differentiate using power rule, you get a plus. So you get positive 1 over x squared. The denominator, we get negative 1 over x squared. So we have a cancellation, but we're left with a negative. Right, so now we can easily evaluate this. As x goes to infinity, you're left with negative 1. That's not your answer, because remember, you started off with the, well, we're finding the limit of the log of the function we're interested in. Log is continuous, so you can bring the limit statement inside the log. And then get rid of the log by exponentiating both sides. So you get the limit of y, right, where y is exactly that function. You can check the other ones, but I believe this is in fact 0. And this might be 1. Let's check that one. So 1 minus. using multiples. X goes to, yeah, so this would go to 0. So e to the 0 is 1, so that's correct. Cool. This is 1. All right. We did all such examples. Right, so you might get something that's not so standard, right? You might get something more inventive, like this is going to be equal e to the 8 apparently. So. But it's the same procedure, right? As x goes to infinity, you get infinity to the 0, so that's actually another indeterminate form. Decouple the exponent from the base, which apparently is my new favorite word, decouple. By, let's do it this way. Right, so this way we get 0. That doesn't make sense, right? How does that make sense? Oh, I think maybe x goes to 0, that's the problem. That makes better sense. Right, so we would get 1 to the infinity. So we take logs. Now we get 0, 0. X is already in the denominator here, notice. So exponential is continuous, doing the limit statement inside. You get 0 over 0 in the exponent, so use L'Hopital's. Not too much fun. And then the derivative of the denominator is 1. So is that good enough? Do we get 5 over 1? Yeah, that's good enough. Right, so as x goes to 0, the numerator goes to 5. The denominator goes to 1. Which, yeah, I don't know when it just happened. Yeah, e to the 10. All right. I'll just leave this one on the answer key. But this is a fun one to do. Apparently this is e to the negative 1. But same idea of logs. All right. And finally, I guess we have some optimization problems. Constrained optimization. In other words, we have two equations. We have one function that we want to optimize, maximize, minimize, and another equation constraining variables. So let's just do a standard one. We have a rectangular box, open top, and we also know that the width of the base width is three times thrice the length. Seems pretty words there. So width is thrice the length. And we want to maximize volume. Given that we only have so much material, find the largest values of maximum. It's 2022, that's it. Like the problems. Square feet. We have the total square footage is only that much. Now, if they had given you, well, so we have to come up with our a function that our objective function that we want to maximize. So let's draw a box. Right, and what are the dimensions of that box? Well, I guess maybe x, y, and z, if you will. Length, width, height. So the volume of that box is actually a function of three variables. But we're going to reduce it, right? Because we have some other information. So this is our volume function, and we want to maximize this. What are some of the constraints? Well, with the width, which is, let's say, is x, is 3 times the length, so y. So x would be 3y. What's another constraint? What's the surface area, right? I mean, it's just how much material we have to construct this box with an open top. All right, so the surface area here is another constraining equation. We have the bottom square or rectangle. We have 2 of these sides, right? 1 on either side. And then the front and the back side, so that would be x times z. There's 2 of those. Okay. And no top, so that's why there's only 1 bottom. And that's 2022. Right, so now we can start replacing, right? For example, we can replace x with y. Whatever you have to do to get your objective function and the thing you want to maximize here to be a function of just a single variable, right? Okay, so now looking at this equation, I know that I can replace x with 3y. Oh my gosh. Do you see how I messed up? X is 3y. Okay. So now we have x is 3y. So that's that, y. And what can we replace z with? Well, if you look over here, you could we could have saved a lot of time by simply calling this 3y. Does that make sense? I should have just done that. But now we can solve for z in this equation. And then we, what time is it? Oh, I gotta go. And then we plug that in for z, and so that would be, and then you have a fun function to differentiate. Good times differentiating. We can even simplify.
Well, you can eliminate the y from the denominator.
Yep, one of the y's goes out. And you probably distribute, right? So in the very near future.
Y minus 9y cubed.
Right, and then you just optimize that function, knowing that y is a positive number, by the way. So you want to differentiate. But it is, it's 4, so I need to be elsewhere. Set that equal to 0, solve for y. So a y would be square root of 6,066 divided by 27. And then once you know y, you can go back to your volume function to get the max volume. Maybe you want to also use the second derivative test to confirm that this is indeed a maximum, not a minimum. But it's obvious from the picture that this cannot be a minimum, right? Because you can easily see what the minimum volume would be if you just let y go to 0 and z get large, so that volume would go to 0. So this must be a maximum. But you probably want to use a second derivative test for your greater. Show that at this value of y, the first derivative is 0, but the second derivative is, well, if you want a maximum, what do you expect the second derivative to be? If you have a maximum for your function, you expect the second derivative to be negative. So second derivative test is what I'm saying. Okay. There's also the antiderivative thing. So if you know your derivatives, you should know your antiderivatives. I would look over that section. All right. Maybe just another thing. What if they 24? Just how to set this up. So find the point, because this is another case where you have to make up your own function even to maximize or minimize. So find the point. Oh, and for the box, if they gave you a cost function, would you be like, so how much it costs to build each side of the box? Would you be maximizing or minimizing? If they said each side of the box costs this much money,
you'll be minimizing.
Right, because you want to minimize, and it's probably going to be the material use. The volume would probably be fixed. It'd be something like, you need to design a box to store this much volume.
And you have to minimize.
Use the least material or reduce the cost, at least, of production or something like that. So that would be a minimization problem. So find the point on the curve closest to, and then pick your favorite point, but we'll make it easy, closest to the origin. All right, so what's the function that you want to, it's obviously going to be some sort of a parabola, right? Something like that. Except I do not know why it opened that way. Some sort of parabola, let's say, with a y-intercept 40. 40 divided by 8. So that's kind of the picture of the curve, and we want to find a point on the curve which is closest to the origin. So what's our objective function that we know? What's the function that we want to optimize in some way? Closest, yeah. It's the distance between the 2 points. A point on the curve, that's which we don't know right now, so we just use x and y. And the origin, which is just the 0, 0. So the distance formula, and I would just use distance squared. So distance squared. If you minimize distance, you've minimized, if you minimize distance squared, you've minimized distance. The x squared plus y squared, right? So that's, we would make that our function of 2 variables. However, it's not really a function of 2 variables, because what is a y? Well, y is on the graph of this curve, so we know y would be 5 minus an eighth of x squared, right? If you solve for y over here. So it's really just a function of x, if you know how to replace y. All right, and then you would optimize the way you usually do. Find the derivative, find critical points, and so on and so forth. Set that equal to 0, solve for x. Anyway, unfortunately, my time is up. So thanks everybody for sticking out for 3 hours. You guys are crazy. Be better off just doing problems on your own, really. Okay. Good luck on the test. See you on next week. Thanks, guys, in online.